So for a rigid body to be in static equilibrium, the object must be both translational equilibrium and rotational equilibrium. Do you know what that means? What does it mean for something to translate? In physics terms, what does it mean for something to translate versus to rotate? To move how?
Moving
linearly, side to side or up and down. What does rotational mean?
on an axis.
To turn on an axis, around an axis, right? Okay, so translational equilibrium means there is no linear acceleration. So does that mean it could move? Yes. It just means that it can't be speeding up or slowing down. So that means it's either not moving or it has a constant velocity, right? So translational equilibrium, no motion or constant velocity. What it really means is, in terms of Newton, it means that the sum of the forces, which we know as ma, is equal to what? 0. This is the big idea for translational equilibrium. The sum of the forces is 0. Now, rotational equilibrium means there is no rotational acceleration. Now, instead of, it could either mean that it's not rotating or that it's rotating at a, yep. Notice I said circular velocity. What do we use for circular velocity? Omega. This guy, the W, right? Omega. So instead of saying the sum of forces is equal to 0, what the rotational analog to force is torque, okay? So we say the sum of the torques is equal to 0, okay? And remember, torque is F times D, isn't it? Or F times R, if we're really talking about the relationship there. So any questions so far? This is all stuff that you've just seen in that little demonstration, okay? Picture paints 1,000 words, doesn't it? So torque, technically speaking, is the measure of the force that makes an object do what? Oh.
Rotate.
Yeah. Think about it. If we're talking about a force, we are looking at, and I want you to look at it from this perspective, we have some pivot point here, don't we? Notice that, like for a wrench, the part that comes in contact is a distance away, some distance r, away from that pivot, the handle, right? That's what's going on. So we're going to hold the end of the wrench and we're going to move it, aren't we? Well, the force is going to be applied pretty much perpendicular to, or at some angle to that wrench, isn't it? I want you to think about it. If we don't have very far that we can move, you guys who do a lot of auto stuff, if you're really trying to unstick a bolt, you got to have room to be able to move that end of the wrench around, don't you? If you've only got a little bit of space, it doesn't work very well, does it? You have to do it just a little bit, and it takes a lot to do it, and you got to reset it and do it a little bit and do it a little bit. Whereas if you can really get it, we call it a torque wrench. To torque it, you get a lot of distance and a lot of angle to move it through. Okay? Both of those play a part. So this is something, so we're talking about the angle right here and the force. So we're applying a force some distance away from a pivot. So this thing depends on what? The torque depends on the amount of force and, yep. So the amount of force, that would be a magnitude. And the distance from the pivot, right? Now the pivot is also often called the axis of rotation. That's where it's going to be turning, isn't it? Now, magnitude of the torque. Torque, which is the Greek letter tau, that's that funny looking T. It's like a cursive T almost. Okay, so does everybody see that is what it looks like on your formula sheet? It is in the first column of your formula sheet. If you look, there is tau. Look about midway down the first sheet, you'll see tau down there somewhere. First column. And you'll see this. It says FD sine theta, doesn't it? Yes? Did you find it? Emma, did you find it? Yeah. Did everybody find it on their formula sheet?
It says RF, but that's like...
Okay. All it says is RF?
Oh, no, it says...
It's R perpendicular, and then T sine theta. That's fine. So R perpendicular. That means the radius is perpendicular to the force. R F sine theta. Now, here's the thing. If F is perfectly perpendicular, then what is the sine of 90 degrees?
0.
Sine of 90 degrees is 1, so that part goes away. So if it's 90 degrees, if F and R are 90 degrees to each other, then it just becomes FR, okay, or RF, because the sine theta goes to 1. If it is more than 90 or less than 90 degrees, then we have to figure out what the angle is from 90 degrees. Notice that this becomes FR sine theta, but notice where theta is. Theta is the amount of degrees between 90 degrees and where the force actually is. So it's not this entire angle from R all the way around, it's just how far it is from,
B to the perpendicular.
yeah, from 90 degrees to wherever the force is going, right? That's what theta is. Now notice what it says right here. What does it say? Only the component of the force is perpendicular to the axis of rotation causes the rotation. So I want you to think about, that's why we say sine theta. Because if you were to look at this as, this way. Yeah. If you were to look at it this way, here's my right angle, right? Wouldn't this part right here, just the part that's perpendicular, correct? Is it that way or the other way?
Force is going down.
Yeah, well, the force is going out. The force would be going this way.
Are you recording this?
I am recording it. All right, so now direction. Let's talk about direction. If you've got to go, I'm recording it and I'll post it before I leave today. Direction. It has a direction and a magnitude. Notice the direction. You already got the magnitude. What are my directions? Clockwise or? So we either do CW or CCW. Clockwise, counterclockwise. Clockwise being, of course, the direction the clock hands turn, counterclockwise being the other way. Okay? Counterclockwise is positive torque. So this would be my positive torque. Clockwise would be negative torque. Okay? So let's talk about what it would look like for this thing to rotate counterclockwise. How would the arrows have to go for this thing to go counterclockwise? I want you to think about it. This would have to be this way, right? And this would have to be this way. Bye. Good luck on your game.
Thank you.
Uh-huh. Wouldn't this make it go counterclockwise? Yes? No? Mm-hmm.
Yep.
So clockwise would be the opposite. So clockwise would be this end going this way and this end going the other way. So this would be clockwise. So this is a positive torque and this is a negative torque. So you just need to remember, if it's going against the clock, it's positive. If it's going with the clock, it's negative. I don't know why the convention is that way. It would make more sense to me if it were the other way. With the clock, it's positive. Against the clock, against negative, but it's not. It's the other way around. Yep, right hand rule. That's exactly why. And that's an easy way to remember it, guys. Take your right hand and make your right hand go counterclockwise. Turn counterclockwise. Which way is your thumb pointing? Up. There's your torque. So the right hand rule will tell you whether it's positive or negative. So if you're rotating, if you want your thumb to point up, your hand has to be rotating counterclockwise, doesn't it? Now, rotate your hand counterclockwise with your fingers following. You have to flip your hand over, don't you? So now which way is your thumb pointing? Down. So clockwise is down, counterclockwise is up. Thus, righty-tighty, lefty-loosey. Okay? That's the way it works, with screwing stuff in and unscrewing stuff, right? Everybody always remembers it. Right hand rule. So this positive torque, negative torque is your right hand rule, and it's the direction your thumb is pointing, isn't it? So it's an easy way to tell. Correct? Okay. So are we good so far? Now there is a relationship between distance and the force. And you saw this in your lab. So what is the what did we figure out about the relationship between distance and force?
The further the distance, the greater the force.
No, the further the distance, the less force you need to do the same amount of torque, right? Think about it. If your torque is equal to FD, as F goes up, then D can go down, can't it? To maintain the same torque. So if I have less force available, I have to get further away from the pivot. If I have more force available, I can get closer to the pivot, can't I? And this is our door. If we try to open that door exactly at the hinges, nearly impossible. Caden, do me a favor. Go to that door back there. Be very careful with your fingers. Grab it. Wrap your fingers around inside that crack right there and try to move that door right at that crack. Don't be afraid. You won't pinch your fingers or anything. Try to move it. It moves, but it's... Now, don't pinch your fingers. Now, was it easy? No. Now, if you go to the handle and move it, we've gotten further away, so easier or harder? Easier. Why that was because as we reduced the distance, or we increased the distance away from the pivot, we could then reduce the amount of force we needed. Does everybody get that? The hinge on the door and where the door handle's placed is totally that. Okay, so a force applied further away from the center creates a greater torque. A force applied closer to the center creates a smaller torque, doesn't it? In other words, it's easier to open by pushing the opposite side of the hinges rather than at the hinges. Units of torque. What is the units of torque? Yes. How do you know it's Newton meters? Yes. Since torque is force times distance, force is in newtons, distance is in meters. What else do we know that is Newton meters? A Newton meter is a joule, isn't it? That's energy. It is a unit of work. So torque technically is what? You'd think it would be, but it actually has no relationship to work whatsoever. I like to point that out, though, because this looks like it would be a joule. It's not. We do not call it a joule. We call it a Newton meter, and it is not related to work, even though the units are the same. It's very strange, isn't it? One is not divided. Newton meters. Work is Newton meters. Joules is Newtons times meters. You're thinking of newtons divided by meters. That's actually what? Isn't that a spring constant? Mm-hmm. All right. So let's look at this. Bob the Builder. I love Bob the Builder. Uses a wrench to tighten a bolt. He applies a 17 Newton force 25 centimeters from the bolt at an angle of 37 degrees with the axis of rotation. Okay? Calculate the magnitude and direction of the torque of the bolt. Well, is this perpendicular? No. So we have to use this angle. That's our theta, isn't it? We've got an R and we've got an F. So FR sine theta. So the force was 17. R is 0.25 because it's 25 centimeters. And then times the sine of 37 degrees. Now we also need, notice that it says the magnitude, but what else does it say? Direction. So we want to know whether it's going to be pivoting clockwise or counterclockwise, don't we? Well, in this case, it's pretty easy because there's only one force, isn't there? So which way is this thing going to rotate? In the direction of the torque, isn't it? So the torque's going to be going this way, isn't it? So that's going to take it counterclockwise. So it's going to go counterclockwise. And what do we get? 17 times 0.25 times the sine of 37? So 2.56 Newton meters. Okay? Now, look what it says next. Pivot points. Some objects have a natural pivot point. Like if you're doing this guy right here, where's the pivot point? If we're taking a wrench to a bolt, obviously the bolt head is the pivot point, isn't it? Because that's what we're turning. Some things don't. So we got to figure out what it is. Any place can be selected as a pivot point, guys. We can pick the pivot point to be wherever we want. Now, some pivot points make more sense than others. A lot of times we take the center of mass to be the pivot. Well, not always. You can pick in a problem where you want it to be. Now, here's the thing. I would pick one of these points to be the pivot point. One of the places the force is being applied. Do you know why? Let's say we pick the pivot to be here. How far away from that is, how far away is force 2 from that pivot point then?
It's like right on top.
So it's 0, isn't it? So how much torque is actually being applied at that point? 0. So we can take one, by placing the pivot at one of the force points, if it doesn't tell us where the pivot is, then we take one of the things out of the equation that we have to calculate, don't we? Does that make sense to everybody? So you can place it at any point where a force is applied or at one of the ends. Typically, a point where one of the forces is applied is a good idea because then it makes the torque from F2 would be 0. Get it? Now, which way this guy is pivoting depends on which one of these two forces left over is stronger. Does that make sense to everybody? These two are opposing forces, aren't they? Whichever one is stronger is the direction that it's going to cause that thing to move, isn't it? Overall, it's going to spin. So if we all of a sudden drop both thumped both of these, the ends, because the force is going up, right? If we thump both of the ends, the end we thump the hardest is the direction it's going to go overall, isn't it? Now, some of it's going to counter itself, isn't it? So things going clockwise are going to be minuses, and things going that cause counterclockwise rotation are going to be counted as pluses, aren't they? So the signs will tell you. So let's do some rotational equilibrium. Sum of clockwise torques equals the sum of the counterclockwise torques if it's in equilibrium. Doesn't that make sense? Rotational equilibrium means it's either not rotating or it's not going to rotate and it's not going to accelerate and get any faster. It doesn't mean it's not rotating. Think about it. RPMs and a record player. It's still going around and around and around, isn't it? It's not accelerating though. Now, some DJs move the record themselves, don't they? Makes that sound? Whatever it is. But anyway, makes that scratchy sound. That is from them applying additional torques. They're changing the rotational rate, aren't they? Every time they touch the record, they change it and drags the needle on the record. That makes a sound because the needle transmits the sound from the record on. All right? So, if a clockwise torque and a counterclockwise torque are about the same pivot point, an object will not rotate about the pivot point and is in rotational equilibrium. That's the idea behind a mobile. Anybody have a little brother or sister? Little baby brother, little baby sister? What do you hang above their crib sometimes to entertain them? Little mobiles, they're little sticks and they hang with strings and they got little stuffed animals or fish or shells or whatever hanging above them, don't they? And they sit there and they look at them and they just stay all nice and balanced. Did you ever wonder why they were all nice and balanced? They're practicing rotational equilibrium there. They've got the different masses hung at different points on the stick to counteract each other. Okay? We can do a whole system like that if we know enough about the masses and how far away they are from the pivot point of the main string. Okay? We can keep everything nice and balanced. So let's look at and check and see if this is in rotational and translational equilibrium. So here's my question. Is this guy in translational equilibrium? Is there any force being applied that is going to make it go left or right or up or down? Let me give you a hint. Is it on a pivot? Sure. I think that's just where there's possible pivots. Remember, at the end or at one of the points. It doesn't matter which one we pick. So tell me whether or not this thing is in translational or rotational. Is it in translational equilibrium? If we pick one of these as a pivot point, if it's stuck at A, can it go straight up or down? Can it go straight side to side? No. So it is in translational equilibrium. Do you agree? Okay, so it is in translational. Now, for rotational equilibrium, guess what we have to figure out? We got to look at for rotational, we have to look at the sum of the torques. So where would you like your pivot to be? Let's pick it at the end this time. Let's make A be our pivot. So for every one of these, we need to find the torques, don't we? Let's call this 1, let's call this 2, and let's call this 3. So we're going to do the sum of the torques. In other words, we're going to take torque 1 plus torque 2 plus torque 3. If this thing is in rotational equilibrium, all of those added up should add up to what? 0. So to figure out torque of 1, we're going to take the force times the distance away from the pivot, aren't we? So what is the force? And the distance away is 1. Now, is it making, if we just look at that force, is the stick going to go clockwise or counterclockwise? Counterclockwise, which means it's a positive or a negative torque? Positive torque. So this is positive. Now, let's look at 2. Torque of 2, it is 20 newtons, and how far away is it from the pivot? No, it is not 2 away from the pivot. It is from here all the way to here is how far? 3. Now, looking at that guy, is that guy going to make it go clockwise or counterclockwise? Clockwise, which means it's going to be, what's its sign going to be? Negative. So minus. And then we do torque 3, which is 8. And how far away is it from the pivot? Yep, this is all the way from here to here is 6. So 8 times 6. Is it going to be positive or negative? Why positive? Counterclockwise, right? It's going to make it go that way, won't it? So this is positive. So we have 12 here minus 60 plus 48. So you tell me, all of those add up to what? 0. 0 newtons, doesn't it? So is this in translational equilibrium, or rotational equilibrium, excuse me?
Yes.
Since this adds up to 0, since the sum of the torques is 0, it is in equilibrium. Do you see how this works now? All right. Anybody have any questions up to this point?
If you put it at point B.
All right, let's put it at point B. If we put it at point B instead, just out of curiosity's sake, that would be this guy, 12 newtons. Now, how far away is it from the pivot? So it'd be 12 times 2. It's going to make it go from this pivot, it's going to make it go this way, isn't it? Clockwise, so that will be negative. And then how far away is this guy? This one is at 0, isn't it? So if it's at the pivot, is it going to rotate it? No. Won't, will it? So that one doesn't get included. So now we do the other one. The other one is what? 8 times 3 meters away? Do you agree? And this one's going to make it go counterclockwise, so it's positive. This is negative 24. This is, which is still 0. Does everybody see that it does not matter where you place the pivot? If it's in equilibrium, it'll be in equilibrium no matter what. Make sense? Kind of cool, isn't it? So it doesn't matter which one you pick as the pivot. Pick one and move with it. I probably would have picked this guy as that because it's less things to multiply and add up. Okay? But do you see it did not matter which direction, which place I picked. All right, so let's move on and let's look at something a little more difficult. Now we got a meter stick. Okay? Uniform meter stick weighs 25 newtons. An 80 newton weight is hung at the 20 centimeter mark and a 70 newton weight is hung at the 90 centimeter mark. Okay, so here's the thing. We have a meter stick that weighs something. That has to be included. We use what we call the center of mass. The center of mass is going to be at the center of the meter stick, isn't it? So let's draw a meter stick. Let's do a little meter stick here. This is 0, and this is 100 centimeters, isn't it? Would you agree? 1 meter is 100 centimeters. So where exactly is the 25 newton going to be? Right in the middle at 50, isn't it? So we've got a 25 newton force going down here at 50 centimeters. We've got an 80 newton weight hung at the 20 centimeter mark. So at the 20 centimeter mark, we got 80 newtons hanging this way. And where else? At the 90 centimeter mark, which would be right here, we've got a 70 newton. Now it wants to know what is the magnitude of the upward force needed to balance the meter stick. So the first thing is this thing in balance? It's not, is it? So where would you like to pick the pivot to be? Okay, good. We're going to pick our pivot to be right here. We'll put P for pivot. That means we do not need to include this in our calculations, do we? Yes? Okay. So Now we got to figure out, we got some mystery weight to balance the meter stick. So first things first is I would like to figure out what the torque is at this point. What is the torque right here? 80 times what? Why 30 centimeters? Yeah, that's this distance right here, isn't it? This is 30 centimeters. So 80 times 30 is what? It should really be 0.3, shouldn't it? So this is what, 24? 24 Newton meters, right?
Should it be negative?
Ah. Should it be positive or negative? Which way is this going to make it rotate? Is it?
Oh, no, it's going down.
It's going down. So this is going to be positive because it's going to make it go counterclockwise, isn't it? Does everybody get that? Good for pointing that out, though, and asking. So now let's deal with this guy. Let's deal with the torque over here. What is the torque at 70 newtons going to be? The force is 70 newtons times how far away is this from that center point? This is 40 centimeters, isn't it? So this is going to be 0.4, which is going to be what? 28 Newton meters. And this is going to be negative, isn't it? So here's my question. This thing is going to rotate right now, isn't it? Which way is this thing going to rotate? Clockwise, isn't it? Which means that which side do I need to put the extra weight on, the mass on, to keep it from rotating clockwise? Do you understand what I'm saying? If I've got a lot of mass on this side, it wants to, right now, this side's going to outdo this side, and the whole thing's going to start rotating, isn't it? So do I need it on the right side or the left side? Ah, upward force needed to balance the meter stick. Okay, so we're going to have to put an upward force on this side, aren't we?
Or downward side.
Or downward on that side, aren't we? Well, since it wants upward on this side, so we're going to have to put something here, aren't we? Somewhere? So we don't know how much it is. Needed to balance the meter stick. Okay, well. As long as it fits on, right? So we know there needs to be an upward force somewhere here, don't we? Somewhere over here? We just don't know what it is, do we? Do we know where it is?
On the right side.
We know it's on the right side somewhere. So let's figure out what it is.
You can do 10 meters going up 27 meters from maybe on the right side. Do 20 meters going up 27 meters on the right side.
Well, here's the first thing we know. Because we've got two unknowns here, don't we? The sum of the forces has to equal, in the y direction, has to equal 0, doesn't it? If the sum of the forces isn't 0, then isn't this whole stick apparatus going to move up or move down? Think about it. We want this to be both in translational and rotational. So this is what allows us, since we have two unknowns, this is what allows us to figure it out. So let's figure out what we have going in the downward direction and what we have going in the upward direction. Does that make sense to everybody? Yes? No? What forces do we have going down here? We have 4 forces total. One we know, and one we don't know. Three of them are going downward. The other one has to be going which way? Upward. So for these to equal 0, then we need this guy, mystery guy, F, to be big enough to counteract 80 and 25 and 70. Does everybody understand why that is? If the force, I've got some things hanging here and some things hanging here that want it to rotate. But if the force is too much going upward, it's just going to carry everything straight up, isn't it? Even if it's rotating some, it's still going to move it up. So does everybody understand that the force is pressing downward? If they don't equal the force pressing upwards, that it moves translationally, and that's not good. So we even those out so it doesn't move translationally. That's why I said f of y has to equal 0. All right, so what does this have to be to zero out all the rest of those things? And I shouldn't call this x, I should just call this f. It has to be exactly 175 newtons, doesn't it? What happens if it's less than 175 newtons? The whole thing moves down, doesn't it? In other words, if I have 3/4, 175 newtons pressing down and less than that pressing up, whole thing's gonna move down, isn't it? If I have more than 175 pressing up and 175 pressing down, the whole thing is going to be moving up, isn't it? So it has to be exactly equal up and down. Yes? No? Okay, that's the translational portion of it. Now let's get to the rotational and figure out where it needs to be placed. This is actually the answer to part A. In other words, forces up have to equal the forces down. Does everybody understand that? And everybody understands why that is now. Okay. Now, where should the force be applied has to do with the rotational part, doesn't it? Yes? All right. We will finish these notes up on Friday. Okay? Is everybody good? All right. You don't have any homework yet. We're going to finish the notes up with the examples and everything on Friday. And then we'll go from there. Okay? How you feeling so far about torque and equilibrium? Neutral. Did the lab help? Good.
It was very